Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is solving problems on charge quantization, J.J. Thomson's experiments concerning the discovery of the electron. First, let's do a quick recap of the concepts related to J.J. Thomson's experiments and charge quantization. Thomson conducted a series of experiments on the cathode rays that eventually led to the discovery of the electron. These experiments played a significant role in the understanding of the structure of the atom. In Thomson's experiment, the charged particle, namely the electron, of course they were thought to be cathode rays back in the days, passes through a region containing crossed electric and magnetic fields and impinge on a fluorescent screen, producing flashes of light. The electric field is basically used to accelerate and bend the beam of electrons, basically manipulating the electron beam, whereas the magnetic field is used to bring back the electron beam to its original position, kind of balancing two forces, right? Electric and magnetic forces on the electron beam. Now the force on the electron is the Lorentz force, which is given by this equation, where F suffix Lorentz is equal to the charge on the electron E times the electric field vector, right, plus V cross B. This is the velocity vector cross the magnetic field vector B. So we can see this as two parts, namely the first part involving the electric force, that is E times E magnitude wise, and the second part involving the magnetic force, which is EVB. Right. Now the basic experimental setup of the Thomson's experiment looks something like this, where we have an evacuated glass tube containing a cathode and a pair of anodes, and electrons are generated and released from the cathode. Basically they were thought to be cathode rays because of this reason, and these electrons travel from cathode towards the anode, and then a thin beam of electrons are made to pass through to this region where a pair of electrically charged plates connected to an external source of power supply ensures that there is a region where there is electric field, and then these electrons pass through this region and then impinge on the screen. And due to the influence of this electric field, the electron beam bends, in this particular case, upwards and then hit the screen somewhere on the top. But for the electric field, that is when the electric field is switched off in this region, the beam goes straight and hits the screen at the center here. Now what is happening here is schematically presented as well. We can see an electron, for example, moving along the, let's say, positive x-axis, and then let's say this is the y-axis for our diagram, and then you can see this particular region, the region containing the electric field, and of course the magnetic field as well is presented here. If the magnetic field, let's say, is pointing into the page, in this particular case, that can be represented as this, and these are the two plates between which electric field is applied, and electric field points from up to down towards downside, right? And the electron beam can be manipulated and in the presence of the magnetic field, it is possible to tune the magnetic field in such a way to nullify this deflection of the electron beam produced by the electric field alone. So when the electric field alone is present, the beam can be deflected, And then Thomson carried out the experiment in such a way that by adjusting the magnetic field, he was able to bring the electron beam back to its original undeflected position. That is the whole essence of this experiment. And this ensured that he was able to study the properties of the cathode rays or the electrons. Now the angle of deviation of the electron from the original direction, if it is theta, that is in our diagram, if this angle is taken to be theta here, then one can say that tan theta is equal to Vy by Vx, because in this particular region the velocity initially is, let's say, V0, and as it goes through this particular region, it has two components along the x direction and the y direction. So the velocity along the x direction is Vx and the velocity along the y direction is Vy, and the ratio of these two quantities is tangent of this angle theta here. So tan theta is equal to basically Vy over Vx, and which can be written again as the velocity along the y direction is the acceleration that the electron beam undergoes in the y direction, which is a suffix y, times the time t, over Vx is the velocity in the x direction, which is the initial velocity which does not change, which is V0. So when the electron beam starts here, it has a velocity V0 and the Vx is unchanged in that direction. So there is nothing done here in this region to further change this velocity or accelerate the beams. It is not done there. So V0 is equal to Vx. And Vy is equal to the acceleration in the y direction, that is upwards direction in this particular diagram, times the time or duration during which such an acceleration occurs in this particular region where electric and magnetic fields are present. So going by that, we can say that Ayt over V0, which is equal to, again, the acceleration is nothing but according to this equation, Newton's second law, mass times acceleration is equal to the force on the electron in the absence of a magnetic field. It is only electric force, that is small e times capital E, that is replacing Ay here, and then times t over V0, and again this time t can be again written as the velocity V0 is the distance over time, and the time therefore is L over V0. So here instead of t we have substituted L over V0, and then therefore the equation gets modified as E times L over m V0 squared, because already there is a V0 and then this V0 also gets multiplied to that, therefore we have a m V0 squared in the denominator. So this is another important expression for the tangent of the angle of deviation of the electron beam. So here V0 is the initial velocity of the electron, Vx, Vy are the components of the velocity in the x and y directions respectively. L is the size of the electrified plates, by which we mean this particular length is L, the duration during which the beam travels in the electric field, that is L, right, the distance rather, right. So we can further simplify this expression from Lorentz original force equation for the force on the charged particle in the electric and magnetic field. So when the magnetic field is turned on in this particular case to nullify the deflection of the electron beam, then we can say that the Lorentz force goes to 0. So we are equating that to 0. If we do that, then the electric field and the magnetic field, they must be equal. So vectorially, E vector must be equal to negative of minus V cross B. So electric force and magnetic force are forces are equal rather, and therefore we can write the modulus of the electric field is equal to Vx, that is the velocity modulus, times the modulus of the magnetic field B, and therefore Vx can be written as a ratio of the electric and magnetic fields, and since Vx does not change from the initial V0, that is equal to V0, and therefore we can substitute in our original equation here for tan theta. Instead of V0 squared, we can substitute E squared over B squared. If that substitution is carried out in this original equation for tan theta, we can get an expression of this form, from which we can isolate this E by M, that is charge to mass ratio alone, which is written as V0 squared tan theta over EL, which is equal to again E tan theta over B squared L. So this is the final useful expression that we need for solving some problems here. Right. Now the path of the electron and its deviation, there is another important thing, because here we can see that from this diagram, when the electron bends, it goes in a curved path or a circular path, so to say, right? So for that we have to again derive some expressions, right? So here we know that when the magnetic field is used to bend in the absence of an electric field, the magnetic field alone can be used to bend the path in a curvature, and then there is a radius of curvature for this path, right? That is, let's say, capital R. In that case, we can say that the magnetic force EVB is equal to the centripetal force on the electron according to Newton's second law, that is mv squared over R. Therefore, from here we can simplify R as mv over EB, or again E by M is equal to V over RB, where R is the radius of curvature of this path, P is the magnetic field, and V is the velocity of the electrons. Now when these two forces, electric and magnetic forces, are equal, we know that EVB is equal to EE, and then the velocity of the charged particle is already given by V is equal to E over B. Now these are some of the expressions that will be very useful in solving the problems related to the quantization of charge and J.J. Thomson's experiment. Right. There are some useful constants that we need to remember. For example, charge of the electron is E is equal to 1.6 into 10 power minus 19 coulomb. Mass of the electron is 9.1 into 10 power minus 31 kilogram. Then we have proton mass, which is equal to 1.66 into 10 power minus 27 kilogram. Mass of the alpha particle is 6.64 into 10 power minus 27 kilograms. Speed of light is 3 into 10 power 8 meters per second. 1 electron volt is equal to 1.6 into 10 power minus 19 joules. That's the conversion between electron volt and joules. Now with these things in mind, we can proceed to solve the problems related to this topic here. The first problem: in the apparatus of the Thomson experiment, what is the strength of the magnetic field needed to accelerate the electron to a speed of 2.2 times 10 power 6 meters per second, assuming the electric field to be 2.5 times 10 power 5 volt per meter. So here electric field is given. Let's proceed to do this. That is given as 2.5 into 10 power 5 volt per meter. What is the magnetic field? That is the question. So we need to find P from our expressions. The velocity of the electrons is given as 2.2 into 10 power 6 meters per second, right? So we have written around what are the things that are given. We know that there is a simple relationship that connects the electric field, the magnetic field, and the velocity, right? That is E over B is equal to V. We need B here, so B is equal to E over V. The electric field is given as 2.5 into 10 power 5 over 2.2 into 10 power 6, that is given as the velocity. So if we work this out, we get B, and that is going to be 1.136, and there is a power of 10 difference here that goes to the numerator as 10 power minus 1. This means it is 0.1136 Tesla magnetic field strength unit, so which can be written as 0.114 Tesla or 114 milli Tesla. That is the solution to this problem. Right. Let's move on to the next problem. Problem number 2. What is the potential difference that is needed to accelerate an electron to a speed of 1.8 into 10 power 7 meters per second? Compare the results obtained for relativistic and non-relativistic calculations. So here we have to do both the non-relativistic and relativistic calculation and compare the results that is obtained for the value of the potential difference that need to be applied here, right? To accelerate the electron to a particular speed in this case. So we have, let's first do the non-relativistic part. Two parts, let's say. So first part is non-relativistic, so that we can later on compare the values. For the non-relativistic part, we have to use just directly force is equal to mass times acceleration, Newton's equation, which is equated to the electric force on the electron, that is Q times E. In this case, charge of the electron is small e, so we have to say it is E times capital E. Now we need the potential, right? We know that in order for this acceleration of the electrons to occur, the electric field is actually a gradient of the potential, negative gradient of the potential applied across the anode and the cathode. And we can say that in this case the acceleration is a time derivative of the velocity, right? This is small v, right? So we can use these two ideas to try to get to the potential, right? Yeah. So using these two ideas, we can say that of course, if we simplify this, m dv over dt is equal to e dv. Here this is small v for the velocity, here this is capital V for the potential, which is of course negative gradient, so we have a negative sign here. But if we take the modulus alone, then we can say that m dv is equal to minus e dv. This goes as dx here, so we have dx by dt here on the left, and here the dx is no longer there. Now if we can say that this is per se the velocity, right? So we have m v dv is equal to minus e dv. Now we need the potential, so we have to integrate both left and right sides, right? So we have, if we integrate this, we get half mv squared, obviously, which is the kinetic energy. And then if we this just like this integrate, we have ev. Of course, I already told that potential is arbitrarily chosen, so we can ignore this negative sign here, just take the modulus, and we know that now therefore kinetic energy is equated to E times the potential difference V. Now this is a basic expression that we need to get the potential in this particular case. So let's do that. So half mv squared is ev. V is equal to half m over e V squared, which is equal to half. The mass of the electron can be taken as 9.1 into 10 power minus 31 kilograms, and the charge is 1.6 into 10 power minus 19, and then the velocity in this question is given as 1.8 into 10 power 7, right? So 1.8 into 10 power 7 meters per second. So if we simplify this whole thing, we get half into 5.69 into 10 power, these powers are adjusted to be minus 12, 10 powers. And then of course this V squared, right here we have to square this one up. So that would be 3.24 times 10 power 14. Again the powers of 10s are adjusted and this is simplified. The final value that we arrive at is 9.22 into 10 power 2 volts. That's the unit for the potential difference. So capital V is equal to 922 volts. So that's the answer. Now we have to do a relativistic calculation as well. So first we have done non-relativistic calculation. We have to now do the relativistic calculation. In the non-relativistic calculation, we took the kinetic energy and we kind of derived it actually here, and we derived it to be half mv squared, right? But we know that kinetic energy from special relativity is gamma mc squared, which is the total energy, minus the rest energy of the electron, and that is this. So this can be again written as gamma minus 1 times mc squared. This is the expression for kinetic energy, of course, where gamma is the Lorentz factor, which is 1 over square root of 1 minus v squared over c squared, right? So if we just get the gamma first, gamma is equal to 1 over square root of 1 minus, the velocity is given to be 1.8 into 10 power 7 over c is 3 into 10 power 8. The whole thing is squared. And if you simplify this, you would end up getting square root of 0.9964. And that would lead to a gamma of 1.002. This is the gamma factor or Lorentz factor for this particular velocity. We need gamma minus 1, which is basically 0.002, or I can write this as 2 into 10 power minus 3. Now we have for kinetic energy calculations, gamma minus 1 times mc squared, and that is 2 into 10 power minus 3, which is gamma minus 1 here, times the mass of the electron, which is 9.1 into 10 power minus 31, times the speed of light square, that is 9 into 10 power 16, that is 3 into 10 power 8 whole squared. So if you perform this calculation, we get kinetic energy in this case to be equal to 1.64 into 10 power minus 16 joule. So we can convert this into EV because this is in joule units. So we can convert that Ke into EV units, electron volt units. That conversion is done by dividing this particular value in joules by the charge of the electron, which is 1.6 into 10 power minus 19. Now the units will be in EV. So the kinetic energy is therefore equal to 1.02 into 10 power 3 EV, or the Ke is equal to 1.02 kilo electron volt, 10 power 3. So we write it as kilo electron volt. This is the final answer for the relativistic calculation of the kinetic energy of the electron. So by comparison, we can see that the kinetic energy is marginally higher for the relativistic calculation compared to the non-relativistic calculation that we performed earlier. In that case, we got about 922 volt, right? So this can be written in kilovolts as 0.922 keV, right? For the relativistic case, we can see that it is 1.02 keV. Of course, potential comparison, we know that simply it is just dropping this E term, right? So that is kilovolt. 1.02 is the potential difference. So if we want V from there, the potential difference, it is just simply 1.02 kV, kilovolts, right? So that comparison can be directly done in that way, right? So the relativistic calculation is marginally higher compared to the non-relativistic calculation. Okay, the third problem. The initial velocity of an electron entering Thomson's E by M apparatus is 4 times 10 power 6 meters per second in the horizontal direction only. That is the initial velocity of the electron when it enters the apparatus. Right? This velocity is given here. The strength of the permanent horseshoe magnet in the lab is 12 millivolts. That is, once it is in this region between the plates, magnet is used to apply the magnetic field, and that in this case is a horseshoe magnet, and that is kept like this so that magnetic force acting on the charged particles, and that strength is only about 12 millitesla here, the magnetic field, which is used in this apparatus. How much would be the electric field required to produce zero deflection? Because once this beam is manipulated by the magnetic field, the very purpose is to get zero deflection. That is, the electric field initially bends the beam. The magnetic field is used to bring it back to the null deflection or zero deflection of the electron beam. So the first part is how much would be the electric field that is required. The second part is the length of the electric and magnetic fields region is 2 centimeters. This is this region, 2 centimeters. How far the electrons will travel in the vertical direction, that is, it is bending, right? How far it will travel in the vertical direction in this electric field if the magnetic field is switched off. So we can get this theta. That is what we mean by how far the electrons will bend. So we have to get the value for the theta in our expressions. We have an expression for tan theta, remember? We need theta for that expression, right? So the first part, let us tackle the first part. So the first part is the velocity is given 4 times 10 power 6 meters per second as the velocity in this case. The magnetic field of the horseshoe magnet present in the laboratory is 12 millitesla. What is the electric field? That is the first part that is of concern to us. The length of the region where the electric field is applied, the plates, that is 2 centimeters or 2 into 10 power minus 2 meters. We know that there is an expression that connects the the electric field and the magnetic field, which is E is equal to VB, or velocity is a ratio of electric to magnetic fields. Since we know V and B directly, we can calculate electric field here by multiplying these two things. So 4 into 10 power 6 times 12 into 10 power minus 3 Tesla. Since it is given in millitesla, we have to multiply this factor. So that is 48 into 10 power 3 volt per meter electric field. That's the first part. So that answers our first part, the A part. Now the B part concerns with itself with the angle, how far it moves in the y direction, that is tan theta. Let's first do, we have an expression for that. That is the electron charge times the electric field times the length over mv0 square. We have derived this expression in the beginning, so please check that expression. I'm just plugging in the values for the electron charge, the electric field that we have calculated, and then the length that is given. That length is given as 2 centimeters over the mass of the electron, and then the velocity that is given, which is 4, that is so 16 into 10 power square, so 12. So if these values are substituted and calculated, we would end up getting, we get 153.6 times 10 power minus 18 on the numerator, and then (145.6) times 10 power minus 19 on the denominator. Then this finally turns out to be equal to 10.54. That is tan theta, and theta is the deviation. So by how far we mean deviation that is caused, that is theta. That should be tan inverse of this number, that is 10.54, and therefore the final result is theta is equal to 84.58 degrees. So that is the answer we are looking for the part B. Okay, let's move on to the next one. That is the fourth problem. A beam of charged particles of different masses emerge out of a velocity selector arrangement. What is this velocity selector arrangement? Basically, velocity is given by E over B in our expression, right? So the region where the electric and magnetic fields are present, that is the velocity selector arrangement. The magnetic field in this particular case is represented to be pointing into the page, plane of the page, and the electric field is applied in this direction. So this crossed electric and magnetic fields, arrangement of crossed electric and magnetic fields, that is the velocity selector arrangement, because it helps us to select the velocity of the particles by manipulating the electric and magnetic fields, right? So a beam of charged particles are passing through this particular section of the apparatus, and the velocity when they emerge out in this direction, this particular on the right side of this thing, is 2.5 into 10 power 6 meters per second. The particles in the beam are protons, electrons, deuterons, and singly ionized helium atoms. So there are 4 different types of particles: protons, deuterons, which are basically, and electrons also, of course. Second one is electrons, so electrons. And then finally the 4th type of particles, ionized helium but singly ionized, so He+. These are the 4 different types of particles that are kind of mixture of particles that are present here in the beam. So it is not a homogeneous beam in that sense. It is a heterogeneous mixture of these particles. And the magnetic field in this particular case, the B value is given to be 0.4 Tesla, 0.4 Tesla, in a direction perpendicular to the velocity. So if velocity is to the right, magnetic field in this case is pointing into the plane of the page here, so that is B in this direction. So these two are perpendicular themselves. Of course, electric field also is mutually perpendicular to these two directions. It is pointing down. What is the radius of curvature of the path of each type of particle? So we have 4 different types of particles here. What is the radius of curvature for each type of particle? That is a question that is asked here. The speeds are same for all the particles, right? Because it is a velocity selector arrangement. So we have derived the expressions for this at the beginning. So please refer to those expressions for solving this problem. We have a few ready expressions, which is first is the velocity, which is a ratio of the electric and magnetic fields. We also have an expression for the magnetic force being equal to the centripetal force on the charges. And using this, we can write the Q over M. If Q is the charge of the particular particle, that is equal to, because there are 2 V's here, we can kind of cancel 1 V. Basically, that will be V over RB, because this B comes to the denominator here, right? So that is V over RB. Or if you want radius of curvature R, that is MV over QB. QB, or electron for electron, can be written as EB, right? Now the charge of the particles have to be same. Please remember that in a velocity selector arrangement, if you have a mixture of particles in the beam, the only condition or requirement is that their charges must be the same charges. So you can clearly see that in the question, the charges that are given are the same. Electron has a charge of E is equal to 1.6 into 10 power minus 19 coulomb. Proton's magnitude of charge is same, right? Proton's charge. And a deuteron also has one extra neutron in its nucleus, but otherwise the charge is same because there is only one proton, so that is also same. And similarly, He plus, when it is singly ionized helium, it also has now only one charge. So all the charges are same. So we can use this arrangement too. We have what is different for 4 particles then? The mass is different. So we can first calculate this term alone, that is V Q over B. The term V Q over B is the same for all the particles. M is different for each. So we can first calculate this term alone, V over QB, or V over EB, so to say, modulus magnitude wise, right? And therefore this will be V is given as 2.5 times 10 power 6 meters per second. The charge is 1.6 into 10 power minus 19 coulomb. Times the magnetic field in this particular case is given to be 0.40 Tesla. So if you do this particular term, calculation of this term, we would get 3.91 times 10 power 25. Now for each 4 of the 4 cases, namely the electron, the proton, the deuteron and the helium, singly charged, singly ionized helium atom, we can straight away calculate the radius of curvature R by multiplying this particular term with their respective masses, right? So that's the point I'm trying to convey. Let's go ahead and do for each one. Right. So first let's take the case of the electron. The mass is 9.1 into 10 power minus 31 kg. So the radius of curvature R is mass times V over EB, right? And therefore 9.1 into 10 power minus 31 times that value we have obtained as 3.91 times 10 power 25. In the previous page we have done that calculation, right? Here we have done this. So that we are trying to kind of multiply here and get the R value directly. So if we do the calculation, this is 25 by the way. So if the calculation is performed for the electron, that would be 3.56 into 10 power minus 5 meters. So this is for the electron. The second case is for the proton, where the mass is different for the proton. So we write MP, let's say is the mass of the proton, that is 1.66 into 10 power minus 27 kilograms. So R is, if you multiply that 1.66 into 10 power minus 27 by that particular factor, that is 3.91 into 10 power 25. We get R in this particular case to be equal to 6.49 into 10 power minus 2 meters. So this is the result for the proton, right? So in the same way we can continue to do for the other two particles in this case, that is for the deuteron. Let me just finish it here. Deuteron. The value for R in this case is, if you take the deuteron mass to be equal to 3.346, if you refer the tables, you would find that this is the mass for the deuteron, and multiply that with this factor 3.91, then you would get our radius of curvature for the deuteron is about 1.31 into 10 power minus 1 meter, or 0.13 meters. Similarly, the fourth particle that is given is helium plus, that is singly charged helium, which is like the alpha particle is doubly charged helium. So it is alpha particle to which the mass of the electron is to be added. That would give us the mass of the singly charged helium atom. And that mass, if we calculate, that would be 6.64 into 10 power minus 27 kg. And then if you multiply that mass with this particular value 3.91 again, you would get R for the case of the helium singly charged helium atom, singly ionized helium atom rather, is about 0.26 meters. That is the final answer you get. You can do this calculations and verify that you get these answers, right? So that completes our fourth problem. Let's move on to the fifth one. In the Thomson's experiment, suppose that the electric field is switched off. If the electrons enter a region of magnetic field B of length L, show that the electrons are deflected through an angle theta, which is ELB over MV for small values of L. Perform non-relativistic calculations. So what is given here? In the Thomson's experiment, the electric field is switched off. So basically between the plates, now there is no potential applied. And the electrons are entering this region. And there is a magnetic field whose strength is given as B. And this length of this region is L. And then the electrons are deflected through an angle only when the magnetic field is present. And this angle is theta. Right, now we have to show that for small values of this L, that is if this region is small really, then this theta is equal to E times L times B over M times V. So that is the requirement, right? Now we can see that in this particular case, if we draw the axis here separately, let's say this is the initial direction of the electron beam, like this, with the velocity, initial velocity v naught, let's say, or the direction of this is v vectorially, and there is a region in the middle somewhere where the electric and magnetic fields are applied, and this particular electric field is switched off, so only magnetic field is present, and therefore the beam, the electron beam, kind of bends this way. It goes like this, right? And this curvature, of course, we have a radius of curvature, and this angle is theta. Now we can, let's say this distance is, let's say, s. The radius of curvature for this particular thing is, let's say, r. Then this must be theta. This is theta, right? So this must be theta then, right? And this is the right arc of a circle, and this is the radius of the circle, and this is theta, therefore. And this and this both are therefore thetas now. Now the direction of this initial thing is changing. It is now going this way, the velocity of the beam. Now we can write straight away for small values of theta. If theta is small, we can write L and S are nearly equal then, right? So for small theta, this S, particular S here we are taken, right, that is nearly the same as this L, the length of this region, because this is a straight line and this is mildly curving and theta is small, so we can do this approximation roughly, and therefore we can write theta is equal to S over R, right? That is arc length over radius. That is what S over R we are writing here, right? And this can be therefore substituted as L over R, because we have S is equal to L. Now we have already an expression for the radius of curvature we derived, where we equated two forces, right? So please bear this in mind now, and then we go to that particular expression and recall that expression here. That is the magnetic force, because here only magnetic force is present, that is EVB is equal to mv squared over r, right? So we use that and derived the expression for the radius of curvature r as mv over EB, right? And we can use this r there in the original expression for theta. That is, we have theta is equal to, in the previous page, L over r. Therefore L over this I am substituting here r for r, mv over EB here, because this denominator goes to the numerator. So therefore we get for small theta, theta is equal to ELB over mv. And in the question, that is what is expected to be proved, ELB over mv, which we have done. So that completes that problem. Let us move on to the next one. It is possible to make a velocity selector for particles or a mixture of different particles with the same charge according to this equation, QVB is equal to QE or V is equal to E over V, which we have already discussed in a problem as well. For an undeflected passage of electrons through such a velocity selector, what would be the magnetic field needed if the kinetic energy of the electrons is 5 times 10 power 4 eV and the electric field available is 2 into 10 power 5 volts per meter? So what is being asked here? Undeflected passage of electrons. That means if the deflection of electrons is negated by the magnetic field, what would be the magnetic field that would be required if the kinetic energy were to be this and the electric field is this, right? Now we straight away have to do a relativistic calculation in this case, right? Because the potential is already fairly high, so we can do a relativistic calculation for the kinetic energy. So kinetic energy expression is gamma minus 1 mc squared, right? Relativistic kinetic energy expression. So this is given as 5 into 10 power 4 eV, right? And therefore we can say that gamma minus 1 is equal to 5 into 10 power 4 eV, which I convert to joules by multiplying it by 1.6 times 10 power minus 19, which is the charge of electron, so that this eV units is converted into joule units, and then I divide that by this term mc squared, which is the mass of the electron, 9.1 into 10 power minus 31 kg, times the speed of light squared, that is 3 into 10 power 8 squared, that is 9 into 10 power 16. So gamma minus 1, if I do this calculation, I would get 0.0976, right? And gamma is 1.0976, hence, right? This is the Lorentz factor that we have calculated. Now using this factor, we can easily calculate the velocity of the electrons, right? So gamma is nothing but 1 over square root of 1 minus v squared over c squared, or square root of 1 minus v squared over c squared is 1 over gamma, which is 1 over 1.0976, right? Therefore we can square this on the left and the right side, and then 1 minus v squared over c squared is equal to 0.8301, or v squared over c squared is equal to 0.1699. V is equal to 0.1699 square root times c. If you do this, you would end up getting V to be equal to 0.4122c. Of course, if you multiply this c with this factor, that is 3 to 10 power 8 times 0.4122, the final velocity you would get is, in terms of meters per second units, that is 1237 times 10 power 8 meters per second. That is the answer for the velocity of the, right. Now in the question, what is further asked? What would be the magnetic field, right? That is the actual requirement for us. So since we have electric field, we know that the expression that connects the two things, that is the electric field and the magnetic field, is the velocity, right? So V is equal to E over B. We need B, which is E over V. And the electric field is already given as 2 into 10 power 5 volts per meter over the velocity that we have calculated now as 1.237 times 10 power 8. So if this is worked out, we would get 1.62 into 10 power minus 3 Tesla, or B is equal to 1.62 millitesla. Of course, in Gauss units we can express as well, that is 16.2 Gauss. So that is the answer. Let's move on to the next problem. Suppose that the horizontal component of Earth's magnetic field at a point near the equator is 3.5 5 into 10 power minus 5 Tesla. Cosmic ray photons arrive at the equator vertically with a speed of 3 into 10 power 6 meters per second. Calculate the ratio of the magnetic force to the gravitational force on the proton. Sorry, here there is a typo, that is proton. So we have cosmic ray protons arriving at the equator. And they are arriving vertically, right, the direction, and horizontally there is a field at the equator, which is Earth's magnetic field, the value of which is 3.5 into 10 power minus 5 Tesla. The velocity of these incoming protons is given as 3 into 10 power 6 meters per second, right? So you have protons arriving in this direction, magnetic field in this direction, right? Perpendicular direction, Earth's magnetic field, right? These two directions are perpendicular to each other. Calculate the ratio of the magnetic force to the gravitational force on the proton, right? So we first directly can calculate the gravitational force, right? At the equator, we can take the acceleration due to gravity on any mass is 9.8 meters per second squared. So we can calculate the force, which is the gravitational force on the proton, right? That is the mass of the proton times this acceleration due to gravity, that is 1.66 into 10 power minus 27 kg times 9.8. That is a gravitational force, let me call that Fg. That is going to be equal to 1.63 times 10 power minus 26 newtons, right? What is the magnetic force now on this? The magnetic force, which we can call Fm, is equal to EVB. This is the expression for the magnetic force on any charged particles. Here a proton charge is the electron charge, which is EVB. So 1.6 into 10 power minus 19 is the proton charge times the velocity, which is given here as 3 into 10 power 6 meters per second, times the magnetic field at that point. Magnetic field of the Earth at the equator is given to be 3.5 times 10 power minus 5 Tesla. So if we just multiply these factors, you would get 1.68 into 10 power minus 70 Newton. This is the magnetic force. Now the question is asking for a ratio of the magnetic force to the gravitational force. The magnetic force is 1.68 into 10 power minus 17 newtons, and the gravitational force we have calculated it to be 1.63 into 10 power minus 26 Newton. That is what we have done here, right? 10 power minus 26 Newton. Therefore, this comes out to be a factor of 1.03 into 10 power 9. That is the number, the ratio. So the ratio of these two forces therefore is roughly 10 power 9. That's a huge number, right? So the magnetic force on the cosmic ray proton at the equator is 1 billion times greater than the gravitational force on the proton. That is obviously due to the very small mass of the proton, right? So let's move on to the next problem. Kinetic energy of an electron moving in a circular orbit perpendicular to a magnetic field is 45 kilo electron volt. The strength of the magnetic field is 0.325 Tesla. What is the radius of the electron orbit? What is the frequency and time period of the electron motion? Right. So kinetic energy is 45 keV. I am going to write half mv squared is equal to 45 kilo electron volt. So half mv squared is equal to 45 into 10 power 3 times 1.6 into 10 power minus 19. For conversion from EV to joules, I am multiplying with this factor. And then mv squared, or directly I can write v squared as 45 into 10 power 3 into 1.6 into 10 power minus 19 over m, mass of the electron, that is 9.1 into 10 power minus 31, and there is a factor of 2 here, so I am multiplying that on the numerator as 2. Now I've used non-relativistic calculation. Please remember this. A relativistic calculation will yield a slightly different result. We can do that. We have done it in several problems already, where I will take gamma minus 1 mc squared as the kinetic energy, and then I would equate that to this value that is given, and then again get the velocity from the gamma factor. So here I am just doing a non-relativistic one. If you do the relativistic one, you get a slightly different value for the velocity. So if you do this one, you would get finally 12.65 times 10 power 7 meters per second. That is the value you would get here. Right. Now what we need the radius of the electron orbit r, for which we have an expression mv over eb. Here we have calculated v, so we substitute mass as 9.1 into 10 power minus 31 times 12.65 into 10 power 7 for v, times the charge of the electron 1.6 into 10 power minus 19 times the field. The field is given as 0.325 t. So if you substitute these numbers and calculate further, you would get the radius of curvature in this case to be equal to 2.21 millimeters, right? Now we have to calculate the second part of this question. The radius of the electron orbit we have calculated, the frequency and time period of motion, right? We know that this radius in a circular orbit for the charged particle can be equated to the angular velocity. In fact, the angular velocity times the radius of curvature is the linear velocity at this point v, right? So 2 pi f is the frequency of motion, that is omega. So omega is 2 pi f. So 2 pi f times r is our v. We need frequency, so f is equal to v over 2 pi r. V is given already. We have calculated v already, so that is 12.65 into 10 power 7 meters per second over 2 into 3.142. Let's take the pi value as, and then r is 2.21 millimeters, that is 10 power minus 3 meters. So if you substitute these numbers, the frequency turns out to be equal to 9.11 times 10 power 9 hertz. That is the frequency. Of course, time period they've asked, that is 1 over this frequency. If you do that, you get 1.1 times 10 power minus 9 seconds. So that is how fast this electron is going in a circular orbit, and that frequency is a billion hertz, and the time period for one orbit is a nanosecond, right? That is what we can infer from these results. Let's move on to the next problem. Calculate the speed of the electrons of kinetic energy 2000 electron volts. What is the time needed by these electrons to traverse a distance of 5 cm between the plates of the Thomson's apparatus? What is the vertical component of the velocity after passing between the plates if the electric field is 3.33 into 10 power 3 volts per meter? Right, so there are three parts to this question. So we know that in the Thomson's apparatus, the electric field is applied between these two plates and the distance is 5 centimeters over which this is done. That is given here. The kinetic energy of the incoming electrons is given as 2000 eV KE. What is the time needed by these electrons to traverse a distance? So kinetic energy, again I'm going to here, since the kinetic energy is small, that is 2000 eV only, 2 kV, 2 kV. We can use easily non-relativistic calculation. So half mv squared is equal to 2000 eV. V squared is equal to 4000 eV over m, or 4000 times 1.6 into 10 power minus 19, the conversion to joules, times the mass we are doing, and then V finally you will get, if you do this, 2.65 into 10 power 7 meters per second. This is the velocity. Now when it enters here, the initial velocity is V0, and here the horizontal component of the velocity is Vx and the vertical component is Vy when its path changes, right? But Vx does not change from V0. V0 and Vx are the same, right? So what changes is basically Vy. So we can say that the initial velocity V0 is equal to Vx, and that is our V we have calculated, which is 2.65 into 10 power 7 meters per second. Now we need time during which it travels between these two plates, which is distance over velocity. The distance over which it travels by the velocity with which it travels, and therefore the time for the electron to traverse this distance between the plates, that is t, right? And this distance is given as 5 centimeter already, so we are trying to use that here. So 5 centimeter is 5 into 10 power minus 2 meters over this velocity, 2.65 into 10 power 7. So that is 1.88 into 10 power minus 9 seconds, or roughly 1.88 nanoseconds. Nanosecond, right? Such a short duration of time during which the electron is crossing the region of the electric field between the plates. Right, so first part we have answered, that is a velocity part we have calculated. Second part is the time part. What is the third part in this question? Vertical component of the velocity, which we have done. Electric field is given. What is the time needed by the electrons to traverse the distance, also we have calculated. Right. No, we need vertical component of the velocity, so we have used horizontal component here to calculate the the time. So the third part is the vertical component of the velocity, that is Vy. Remember, the duration is the same time for the Vx as well as the Vy. That is, the time taken for the electron to traverse is the same. So velocities of the vertical and horizontal components, velocities are different. So what is Vy? We know that using the Newton's equation, mass times acceleration is equal to the electric field, and we know that Ay times t, the time of travel, is Vy. So we can substitute here m Vy over t is equal to E, right? So if we do that, Vy will be equal to E, capital E, times T over M, right? And therefore we can substitute these values, and Vy is equal to the electric charge 1.6 into 10 power minus 90 times the electric field is given as 3.33 into 10 power 3 volts per meter, right? 10 power 3 volts per meter times the time, which we have calculated as 1.88 nanoseconds, so it is 10 power minus 9 there, over the mass of the electron, that is 9.1, let's take, times 10 power minus 31. So if you do the calculations, you get 1.05 times 10 power 6 meters per second. So that is the vertical component of the velocity. So the horizontal component of the velocity Vx remains unchanged, whereas the vertical component is this value, 1.05 to 10 power 6 meters per second. So that completes this problem. Let's move on to the next one. J.J. Thomson's first experiment. Remember, Thomson performed a series of experiments. Particularly 3 experiments are noted for the value of knowledge that it contributed. Of course, the third experiment was a successful one that confirmed the existence of the electrons in the atom, though the atomic structure was not fully understood. But the first experiment consisted of a beam stopper used to collect the electron beam, stop the beam of electrons and collect them in order to measure the total charge of the electrons collected. Due to the transfer of energy by the electrons, the temperature of the beam stopper rose, and knowing the heat capacity of the material of the beam stopper, it was possible to calculate the number of electrons collected as such by this beam stopper. If the heat capacity of the beam stopper was about 5 into 10 power minus 3 calories per degree centigrade, and its temperature rose by 2 degrees Celsius, what would have been the number of electrons stopped by the beam stopper, given the electrons had a kinetic energy of 2000 electron volt, right? So what is given here in this arrangement of electrons going, this beam of electrons can be stopped using an arrangement called beam stopper arrangement, and then any electron that is impinging on this is going to transfer the kinetic energy to this beam stopper, and therefore this is going to heat up. The beam stopper is heating up basically. Its heat capacity is given, and the temperature rise due to the impingement of electrons. The impinging electrons is given, but a number of electrons are impinging, and therefore the total increase in temperature is only 2 degrees centigrade. Now we can calculate based on this information how many electrons are basically being stopped by this beam stopper. That's the idea here. Now let's first calculate the total change in heat. That total change in heat due to the stoppage of the electrons by the beam stopper total change in heat of the beam stopper is equal to its heat capacity times the change in temperature, right? So heat capacity multiplied by the change in temperature, which is 2 degrees centigrade given here, and heat capacity value is given. So we can just multiply these two things. 5 into 10 power minus 3 times 2, that is 10 minus 2, because this is 10 to 5 calories. That is the amount of heat that has been received by the beam stopper. Now we have been given the electron energy, kinetic energy, as 2000 eV, and therefore we can convert this heat energy of 10 power minus 2 calories as to EV volt, to EV units, right? So that is 1 calorie is equal to 2.613 times 10 power 19 EV. This is the conversion factor. So 10 power minus 2 calories is 10 power minus 2 times 2.613 times 10 power 19 EV. That is 2.613 into 10 power 17 EV. Now 2000 EV electrons are impinging on this beam stopper, electrons of kinetic energy 2000 EV, and therefore number of electrons that are collected by the beam stopper is the total energy change of the beam stopper, which is this number now, by the kinetic energy of the electrons. That would give the number of electrons which we need in the answer. So the number of electrons is therefore basically 1.306 times 10 power 14, because here 10 power 3, I'm just dividing it by 2, and this is the number that we need. That is the answer. 1.306 into 10 power 14 electrons. Those many electrons strike the beam stopper to increase its energy by 2.613 into 10 power 17 eV. That brings us to a conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.